What's going on, guys? Derek here once again from Wilson Audio Labs. Another box from Amazon. Taramps Smart 3. What you guys know about this? Well, you're going to find out in this video. Why are we going to talk about Smart 3? Is it smart or is it a big dummy? Like you know who. Well, let's find out what Taramps says. So yes, friends, this is a smart amp. It does the same power everywhere from 2 ohms down to 1 ohm. It has some smart LEDs so you can watch the power visually. It has RCA inputs and outputs, accepts 4 volts RMS for the input, has large power gauge inputs for power and ground, which is nice. Here you can see their little gauge, their little chart. 4 4-ohm speakers, 3 4-ohm speakers, 4 6-ohm speakers, 2 4-ohm speakers, all give you 3,000 watts. That's what I'm talking about. You can see on the end of the amp here on this one side, it's pretty much standard Taramps. Has RCA ins and outs. It does have a gain control. It has a high pass and low pass. This amp does go up to 10 kilohertz. Also has a variable bass frequency and a variable bass boost. And then we have about 6 gauge for the speaker outputs. On the opposite end, you can see a smart cooler there on the left. You can see the beefy 1.0 inputs, another smart cooler on the right. And yes, this has 1.0 inputs. They listen. Thank you, Taramps. We appreciate that. At the time of the video, you could buy this amp for $265 on Amazon. Check the link below for the current price. In the box, you get a warranty card, small sticker, you get a big sticker that says break my window out and steal my fancy amp. And here's the amp. And it also comes with this neat little display that gives you the on, the protection, and the clipping, and it connects via the phone style RJ11 connector. Here are all 3 amps. You can see the base 3K, the HD 3K, and the Smart 3K. Here are the dimensions, about 238 millimeters by 228 millimeters, or 9.4 by 9 inches, 2.76 inches tall, or 70 millimeters. This amp is identical in size to the MD3000, which we don't have here. Now, we're going to show you the guts of each of the amps so you can see what they're all about. Psych!
Got him! Got him!
Alright guys, so you know I will leave you hanging like that. If you wait until after the dyno test, I have a really detailed technical review of this amp, thanks to Sam from BearVid. So make sure you stick around, check that part out. It's literally a video in its own. He did such an awesome job. So here's the amp, and we were hooking it up, and one thing we did notice is these 1.0 inputs definitely are not for oversized inputs. It's unfortunate because we like to use double 1.0 inputs whenever we can just to make sure the amp has all the power that it needs. So in this case, we just used the Stinger wire, which is standard size 1.0, is not oversized. Oversized wire is not going to fit, so you might have to cut it down a little bit if you do have oversized 1.0. Here we're powering up the amp. You can see all the different things going on from the light on top of the amp to actually the remote display as well. Alright, and here's the time you guys enjoy. This is the RMS power output test using the amplifier dyno from Steve Mead Designs, More Engineering. Going to fire it up right now and do these RMS power output tests. First off, we're going to start with 4 ohms. The amp is rated 2,000 watts at 12.6 volts. One thing I want you to notice is at the far right, you can see the little clip indicator there from Taramps. Matches pretty close to what we got here. 4 ohms, 1,936 watts. So pretty much right at 2,000 watts. Uncertified, we got right at 1,960 watts, 13.36. Again, insignificantly different from the 2,000 watts it's rated. Dynamically, again, all these tests are at 40 hertz if I didn't mention that. We got over 2,000, 2009 at 13.76. I was absolutely blown away by this 91% efficiency at 4 ohms. That's awesome. Now let's try 2 ohms. Now it's rated 3,000 watts at 2 ohms at 12.6 volts. First up, certified test takes us to 1% total harmonic distortion. And there you go, 3,074 watts at 13.3 volts. Got there, barely, but it got there. Uncertified takes us up to clipping point. And you can see almost 3,200 watts, 3,179 at 12.98 volts. Dynamic sends a 40 hertz pulse tone into the amplifier. You can see here almost 3,700, 3,699 at 13.77. Now the efficiency did suffer. You can see 69% at 2 ohms. Sam will talk about that later in the technical segment, so make sure you watch that. 1 ohm, again, it's rated 3,000 watts at 12.6. First up, certified, 40 hertz. 3184. Notice our current pull is less, 298 amps, than it was at 2 ohms. Again, Sam will discuss that. Uncertified 3235 at 13.26. Dynamic now. This one, hold on to your hat here. 5063, 5363. Crazy. Now notice the efficiency at 1 ohm is better. 80% efficient at 1 ohm. Here are all the results. You can see I tested all the way from 4 ohms down to 1 ohm, including 1.3. If you guys want to see more, half ohm, 0.8, give me a thumbs up. If I get 3,000 likes, I'll do it. Let's do a subwoofer demo. Bass Outlaws, 3 kinds of bass. Bass Syndicate. Killing it. You can't even hardly see the VU meter. All right, next up we're going to talk about the technical specifications and the inner workings of the Smart 3 compared to the Bass 3K and some of the others. But instead of a big dummy talking about it, I have enlisted the brain power of Sam from BearVids, who's an awesome technician. He's going to talk about what he thinks of this amp. Make sure you check it out.
So, as many of you will be aware, amplifiers offering constant power across a range of impedances are nothing new, and you only need look back to the release of the popular and well-received JL Audio / range of amplifiers to see this. However, this is a notable release due to the following which Taramps carries. Whether you like them or not, they are helping drag car audio amplification in the direction it needs to go, away from ancient inefficient half-bridge designs and into the more current times with low RDS MOSFETs, fast powerful drivers, full bridge architecture and efficient operation. On first glance at the guts, this appears to be almost identical to the Bass 3K, and it pretty much is the exact same amplifier with a few modifications. Let's walk through these and play spot the difference. Both amplifiers use a PIC chip to control initial health check, power supply dead time, and protection circuits. These chips drive the FETs directly with only a gate buffer in between. I'm not a fan of this, but that's a whole other story, so let's move on. The power supply MOSFETs themselves are different, albeit very similar. Both 40 volts, roughly the same pulse drain current and power dissipation. The CSD parts in the Bass 3K do have the edge though, and have a lower on resistance which allows them to run a tiny bit cooler and are actually easier to drive. I imagine the reason for the change was simply supply availability or cost saving. They're similar enough that performance differences will be negligible. Next is the transformer, which looks kind of the same, but the amount of turns on the secondary winds will be different. The Smart 3 needs to have considerably higher rail voltages in order to produce the 3K at 2 ohms. Remember, as ohm load goes up, the voltage required to make a given power must also proportionally go up. The rectifiers here are the same MUR 1620 as they have enough headroom for both amplifiers. However, the rail capacitors in the Smart 3 are rated for 160 volts as opposed to 100 volts in the Bass 3K, confirming that higher rail voltages are present. The amplifier output and drive circuits are identical. Class D audio pulses generated around here, IRS 20957S output drivers here, and then onto the FETs. Now, you may have noticed that the Smart 3 has more output FETs than the Bass 3K, and I was expecting to see higher voltage FETs but more of them in the Smart 3, because as with most electronic components, the higher the voltage rating, the lower the current handling for the same size part, so you need more of them. But actually, both amps are using IRFB 4115. These are 150 volt FETs, so way above what was needed for the base 3K and are clearly ample for the higher voltage inside the Smart 3. As to why it has more of them is a mystery to me, since 1 ohm operation demands the most current and playing into 2 ohm will require higher voltage and lower current for that same 3K, so the Smart 3 will never have a higher current across the output FETs than the base 3K. I guess Taramps just decided to even out the load and go for cooler, more relaxed operation, or it could be to do with the Smart 3 playing up to 10 kHz as opposed to the 250Hz, so the Class D switch frequency may be higher and the FETs will generally run hotter playing this higher frequency. Let's just look at some numbers real quick. Both of these amps are rated for 3K 12.6 volts 1 ohm, which would require 55 volts RMS sine wave on the output terminals, which is around 160 volt peak potential. However, since these are full bridge amplifiers, each side only requires half of that in rail voltage, meaning we end up with around 85 volts of rail potential, allowing for some load sag. These calculations are with 12.6 volts worth of input, but these amplifiers have a maximum input voltage of 16 volts, and since the rail voltage is directly proportional to the input voltage, we can use a square log correction factor to calculate the maximum rail potential inside at 16 volts, which ends up being around 115 volts rail to rail potential. This is under the 150 volt FET limit, so all fine for the base 3K, but the Smart 3 also does the 3K at up to 2 ohm. So let's look at the rail requirements for that. 77 volts RMS sine, so 110 volts rail potential with 12.6 volts of input, and around 140 rail potential with 16 volts of input, which is pretty scarily close to the FET's limits, guys. Don't run these things at 16 volts. Thus concluding the IRFB 4115 are suitable for both of these despite the voltage increase in the Smart 3. The output filter inductors are in the same location, but you'll notice with a far lower number of turns on the Smart 3 due to it playing up to 10 kHz. The preamp circuit looks to be much the same layout. Just below this, I noticed the Smart 3 had an extra chip, which I believe is responsible for the magic 3K at various loads. The way this will most likely work is by monitoring the current drawn by the output section. We already know that this amp makes 3K at 2 ohms, which is 77 volt sine wave and 39 amps. Now, without any restrictions or fancy circuitry, if you hooked up a 1 ohm load to the amplifier, it would try to produce around 6K drawing 77 amps from the output and more across the power supply, which would be far too much and the amplifier would go up in smoke. So, in order to prevent this, while still allowing 1 ohm operation, an extra circuit will apply a current mode clipping, which is a simple current limiter that when triggered will restrict the sine wave amplitude to keep the current at a safe level. This works kind of the same as a current limited bench power supply. If you set your limit to 10 amps, as your load resistance drops and it attempts to draw over 10 amps, the supply will keep lowering the voltage from 12 volt, 10, 8, 6 as your resistance drops in order to maintain a constant 10 amps. I asked Derek and he was kind enough to shoot me a couple of video clips of the sine wave on his scope at 2 ohms, 1 ohm and with no load connected, just to show you here the difference in how the sine wave is clipped by the amplifier in these different scenarios. So you can see here, this is the amplifier going into clip with no load connected, and as you'd expect, the sine wave just touches the rail voltages and it starts to cap off where the voltage limits inside the amplifier are. When we connect a 2 ohm load, there is no current limiting taking place, so the sine wave is allowed to reach up to those rail voltages, but because we're playing into a load, the top sags down and it's kind of angled because as the sine wave touches the rails, the rail capacitors start to deplete slightly. That's pretty normal when you load an amplifier into clip, so that's a very normal looking kind of clip sine wave shape at 2 ohms. However, when we drop it down to 1 ohm, you can see here that something very strange happens to the shape of the wave, and Derek even exclaimed it here.
It's some weird clipping.
Rather than the amplifier allowing the sine wave to reach its rail volt limit at 1 ohm, instead you can see what the circuit's doing here to limit the amplitude of the sine wave to a lower voltage, allowing the 3K to be clamped but preventing excess current being drawn from the amplitude of the sine wave going any higher. And it looks a little strange, so obviously I've not looked at one of these amps on the bench yet, so I can't confirm exactly what the circuit is doing, but it's limiting the sine wave in a way, and it kind of adds this weird kind of noise to the top of the sine wave where it would be clipping, but it's preventing it going any higher. Very strange shape, but yeah, there you go, just to visualize it a bit easier. This has a few interesting results that may not be obvious at first glance. Many people think that amps like this can cancel out impedance rise or box rise. While they certainly do help, don't go thinking that you can clamp 3K at all frequencies with these things. Since impedance rise is frequency dependent, you'll have one point where your box rise or impedance rise is at its lowest. Example, wired to 1 ohm nominal, the frequency causing lowest box rise is 1.3 ohms, which is usually your box tuning frequency. So if you were using the base 3K, 1 ohm rising to 1.3 would clamp 2300 watts to the sub at its fixed 55 volt sine clip point. The Smart 3's power doesn't drop with higher impedance, so you'd be able to clamp 3K at the raised 1.3 ohms with a 62.4 current mode clip point sine wave, giving you a 700 watt advantage over the base 3K in the same setup. However, since you set your clip point on the Smart 3 here at 62.4 volts based on the lowest point of impedance rise, when the frequency changes and you're now rising to 1.8 ohms, you will no longer be clamping 3K, since to do this you would require a 73.4 volt sine wave. The amplifier can only limit and restrict the sine wave amplitude. It cannot and will not boost it when it detects the current draw is under the set limit. If it did, the output would sound awful, dynamics would be all over the place, plus you'd run into overexcursion issues. Output sine wave amplitude is tied directly to the gain position. As a result, for a given 4 volt line signal, there will be different gain positions required for 1 ohm and 2 ohm operation to prevent you constantly being in current mode clip. Secondly, you may have noticed that Big D's DC current draw figures were a little strange. It drew considerably more current, making 3K at 2 ohms, and less, making 3K at 1 ohm. Why is that? Well, this, my friends, is due to amplifier efficiency dropping badly as you approach its natural rail voltage clip point, and it's why everyone tells you not to run into clip. During the dyno here, the amplifier will have been hanging on the edge of clip, which already will have reduced the efficiency due to the sine wave being so close to the rail voltages inside. This does not happen when used with a 1 ohm load on this amplifier, however, due to the induced clip point being artificial, as the amp is just preventing the sine wave going any higher. It is still far enough away from the hard rail voltage clip point that the efficiency is not affected, thus it can do 3K while sucking less from the car's charging system. Interesting to know. Maybe all amps should be designed like this and they'd last longer. This can all be a little confusing to understand if you're not familiar with basic electronics, so if you're interested in learning more about how and why these things work as they do, be sure to subscribe to my channel as I plan on releasing an in-depth video on this subject soon. Bear in mind that everything so far is speculation, as I haven't personally explored these on the bench myself yet, so it'll be fun to see how much I predicted was right. In terms of build quality and such, no complaints here. These are small and well assembled and do not suffer from vibration damage. The pair of fans should deal with any heat accordingly, and thank God they only come on when needed, unlike the older amps which yeeted all day long. Overall, I think this is an excellent little amplifier that makes good use of methods available to bring high power in a small efficient form factor, and aside from my speculations about the reliability of the power supply section, would have no doubts recommending it to those interested in it.
Thanks for that awesome review, Sam. Next, we're going to talk about the goods and the bads. First up, power output is good. Efficiency at 4 ohms is incredible. Nice variable subsonic, accepts large gauge power inputs. Relatively compact size, cool power LED, and value. Cannot go without saying the value is awesome. Wish it had larger gauge 1.0 inputs. Wish it had 2 RCA ins, 2 RCAs out, so you didn't have to use a splitter. A bass or remote level control would be nice. 24 dB per octave low pass would be nice because I was getting some vocals in my sub. And the plain looks, yeah, it's kind of plain. What can you say? Well, there you have the technical test, subwoofer test, everything you want to know about the Taramps Smart 3. This amp is really incredible for the price. Taramps is just killing it, coming up with new designs, always changing things around, modifying their amps to fit the US market better. It's just pretty incredible here, especially for the price. Not sure about the reliability. I did buy this amp. This amp was not given to me by Taramps, so everything I'm saying here is my opinion and Sam's opinion. Thanks again for everybody supporting me on patreon.com/oldschoolstereo. Thanks to Sam, Joe, Stewart, Vintage Stereo Buff, Legends of Car Audio, Hi-Fi Vega. I'm out of here! Taramp Smart 3, we're going to try certified 1.33 ohms, 40 hertz.